active power in fundamental frequency, okay? Because when we are talking about the fundamental frequency, load cannot be only fundamental. It can be harmonic, reactive, lots of things, okay? So the calculation we calculated from here, that active power can be calculated by this, reactive power can be calculated by this. Apparently we can see Q is equal to 0, here Q is 0, and then we see that, you know, we have actually fundamental frequency here. But now the interesting part of the dq is like this, okay? When we discuss about, yeah, we use the dq, but the reason is that we can transfer the variable from the fundamental frequency to DC value, okay? So now we see that, you know, we have actually load. Load is a nonlinear, very dirty load with lots of nonlinear components. So it's like a grid which supporting the load here, and then we are going to inject AC, DC, ID reference, IQ reference. So to provide this one, if we are going to consider the load current components, so it's ID and IQ, okay? So then ID can be split to ID fundamental frequency plus IQ, ID harmonic frequency. And for IQ DC or fundamental frequency, IQ harmonic frequency. Is it fine? So if someone asks you that I'm going to provide electricity like a grid forming with the active power in fundamental frequency, it means that you need just to create this one as a reference. So your reference will be ID in fundamental frequency. How is possible? I said that, okay, does anybody has any idea? How is possible to because now the current is like this one. But I'm looking for this component. How is possible? Sorry? AC to DC, what do you mean by AC to DC? Use the rectifier? You mean the transfer to dq? Yeah, this is correct. But assuming that we transfer it to dq, so we have ID, IQ. ID, fundamental frequency plus ID harmonic. IQ, fundamental frequency plus IQ harmonic. So if you draw the current ID and IQ, ID can be like this, IQ can be like this. Okay? So this is ID, IQ. And then when we split this one, this can be like ID and IQ, like this. This plus this is this, and for this, it will be ID. This plus this is this. Okay? So what the customer asking us is this value. We are going to provide this one. Okay? Reference current to supply load active power in fundamental frequency. Okay? So what can we do is that. So active power in fundamental frequency. So it means that reactive power is equal to 0. Okay? Then active power, ID, is ID fundamental plus ID harmonic. So it means that this is my ID. We use a low pass filter, and then so what we provide, this part is IA DDC, and if we this one be ID harmonic. Okay, so if we put the measurement here and measure the current of here, and this current we put here, then our system is working as a grid forming. Just provide the active power in fundamental frequency. We are not allowed to provide the harmonic, because if we provide the harmonic for the grid, in fact we inject the disturbance to the grid. Okay? So we inject just the active power, and just we compensate the active power of the load. That's all. So how is possible? So you take, for the simulation, you have the three-phase system, IA, IB, IC. So we give it to Park with the theta of the grid. We get ID and IQ. That's much easy. Okay, then we split the ID, get the DC value from the after filter and put it here as a reference. Then the converter inject just active power in fundamental frequency. Am I right? So, is it clear? Siddhant, did you get it? Okay, good. So this theta is coming from where? Sky. ID. Theta is coming from load. Did you sleep well yesterday? Yesterday. Because you were absent when I explained to you. So, she's lying. From where? From where? Yesterday. PLL. PLL, what is the PLL?
Phase
Lulu. Okay. Okay, Shida. What is PLL? Okay. Yeah. So, and so how it works? You don't know. We provide what? Yeah, grid voltage, and then it gives the omega t, yeah, theta, frequency. Okay, so we get the actually voltage of here, give to PLL, and PLL give the theta to here. Am I right, Siddhant? So why we get the voltage actually from here and we don't get from here or from here? Or why we don't get the current or something like this?
DC to AC, the converter is present there, that's why.
Mhm. So we are going to connect to the grid. So we need the grid voltage as a, yeah. So when then we actually provide by this, we get the DC and put it this and, yes. Okay, good. Do you like to buy ice cream for all class?
No.
Okay, so listen carefully. Then next time you will buy. We are your friend actually. You should buy. Okay, now we go to next part. Calculation of harmonic component of reference current. So, when we have this filter, we have the DC value, then we actually use the original current minus DC value, rest will be harmonic. So if we consider this one as a reference in the axis, in fact converter provide all the harmonic for the load. Okay, so ID is coming go like here, ID, H, I mean the harmonic, supply here, and fundamental frequency ID, fundamental frequency is coming here. Is it clear enough? Okay. So the problem of this type of actually filter is that it provided a delay for the system. So it somehow increased the transient response of the system, so we can consider this like a weakness of the system. But because the application is in load center, so basically for that application, it doesn't provide that much actually sensitivity for the dynamic response. If it was the grid, it was different the story. But for the local consumption, it is not that much important. It is important, but I'm saying that it can survive. They can survive. So now we go to the reactive power. So no, the active power. So now we talk about this story that the main idea is that we inject the maximum active power. So assuming that you have a nonlinear active load, is a combination of the harmonic frequency and fundamental frequency. Okay, so this harmonic current take the 60% of the power which can be injected from the converter to the grid. Okay, but still we have some space to somehow compensate the or provide some electricity in fundamental frequency, but not all of them. So for this case, what should we do? We provide a limiter. Okay, so in your simulation work, you can do like this one. Assuming that you are going to provide the reference current for your converter. Yes. This one, 50 hertz. You are talking about 50, yeah? So now get back to here. Assuming that you have a load, nonlinear load is I D is I D in fundamental frequency plus I D in harmonic. Okay? So my customer wants to compensate the harmonic, but I can give a better solution to him. I said that, okay, let me give this advice to you. You can compensate the all harmonic, but still you have some available power that you can use as active power in your system. So you buy less power from the distribution company. And the customer said, really? So it means that I should pay less to DSO? I said, yes. Okay, how? Let's see. So we have actually ILD. ILD, okay? So we get the harmonic part by the filtering, okay? So like this one. ILD, low pass filter, fundamental frequency, and then this is plus minus ILD in harmonic. Okay? So now I said that, okay, I see D reference is ILD, okay? But then I said, okay, still you have more possibility to compensate some part of active power. So I said, okay, plus P fundamental frequency. How much? For example, 5,000 watt over VD. Okay? So what it say that, compensate the active power in harmonic frequency plus active power in fundamental frequency. So assuming that it is 10,000. So it means that 5,000 is coming from here and 5,000 is coming from here. So it means that in a state of buying 10,000 from the grid, they pay 5,000 because 5,000 is coming from the DG. So it maximizes the profit for the customer side. So how we can do it? We said that, okay, this is ID for the harmonic, but for this I put a limiter with the band of 5,000. Then divided by VD, it gives the ID DC. But ID DC is not the maximum ID DC. It's up to 5,000 watt over to VD. So by this, you compensate all the harmonic component and part of the active power in the fundamental frequency. Only active power in fundamental frequency remained. It can be provided by power grid. Okay? So it maximizes the profit for the customer side. So now we are going to talk about the reactive power. But before that, you see the procedure for the active power, yeah? Now, if we are going to proceed the reactive power, Rakesh, so what should we do? Look at me, my eyes, like a strong man, say that I don't know. Okay? Tell me. What should we do to compensate the reactive power? Should we compensate the harmonic components or part of the harmonic and fundamental frequency of the reactive, and or hold the reactive power? What is your suggestion? Tell me. I will not eat you, okay? Tell me, friendly, I don't know, but this is my idea. I'm not sure. It's like, what? Yeah, but I mean, how much reactive power you prefer to be compensated? Part of that, none of that, all of that. Which one is the best? Okay. Even I give the answer, he's not actually, he's shying. So, any idea? Is it the same for the active power and reactive power? Is it the same? Why? Yes, exactly. I mean, reactive power is different from active power. The main responsibility for the distribution company is providing active power for us. So if we have actually a load with the reactive power or fundamental harmonic frequency, in fact, we are making problem for the grid. So for this case, the best is that we replace reference value based on reactive power both in harmonic and fundamental frequency. So by this we can fix the power factor of the system in unit value. So we don't need to say that no, we should split, use the no. Any reactive power, it should be compensated. So this is different from the active power. So if you have a load, combination of the reactive power, harmonic, active power, then the main, actually, the main priority is not the active power. The main priority is that reactive power and harmonic, and if we have extra power, we can compensate the active power in fundamental frequency. Rest of the remained power can be supplied by the active by the distribution grid. Is it understandable the reason that how we prioritize different actually component in? Okay, good. So, Costa, ¿qué pasa, machote? ¿Todo bien? He's not understand the Spanish. Yeah, what's up, bro? Like this. You never see the Spanish movie? No? Italian. Entonces, molto bella, like this one. No?
Somewhat about it.
Okay. So if you are going to say someone, I love you, what do you say? Te quiero mucho. Okay. Yeah.
Spanish says here,
Te quiero mucho. Yeah. We record this one. Okay. So good. You don't need it. You measure the reactive power and put in the actually. Yeah, because it's combination of the frequency, harmonic frequency and fundamental frequency. Both of them make the damage on the grid, so we should actually compensate there. Yeah. So, any questions so far?
harmonic component of ID as a reference.
Mhm. So it means that we just compensate the ID, harmonic frequency of the ID, okay? But when we have the nonlinear load, it can be combination of the ID and IQ. And then it depends on how much active power and reactive power also needed in fundamental frequency. So if you are going to consider to compensate, it can be active power in harmonic frequency, reactive power in harmonic and fundamental frequency. Then if you have more possibility to inject or available power or enough, then you can think about to inject some active power in fundamental frequency. Or by then you don't pay penalty. Yeah. So this is what we studied from yesterday up to today. Okay? So if you are going to get back to this, so our story started by grid. We have a grid which is providing component for the load. Okay? So load asks about the active power, reactive power, and also harmonic. So it means that the grid provide actually should provide some reactive power and harmonic beside the active power. So it means that the load is not, it's providing something which damage the grid. So for this case, we use a converter. This converter is supplied by a type of actually DG sources. So it can be Win, for example. Then we use the rectifier to change from a AC to DC. We make the voltage regulation, and then we provide the DC AC conversion system to provide power to the grid. Okay? So this converter or inverter is responsible to provide the power in 50 hertz. Okay? So then it should be controlled and provide based on the what we need as a support inject to the grid. So we said that we have voltage, we have inductor, we have resistor, we have actually voltage of the each leg, Vm, V1m minus V1m plus Ri plus LdI to dt plus V1 plus Vnm is equal to 0. Then we calculate the di to dt and then replace the VDC, SVDC in Vnm, and then we see that, you know, we obtain the dynamic model. So up to here we have the dynamic model. So then we decided to transfer it to DQ because DQ could help us to control it faster. So for the DQ, we need to measure the voltage of the grid, point of common coupling, and convert it to the alpha beta. And after that, we use this alpha beta in equation 21.1, which is tangent inverse V beta to V alpha. And based on that, we calculate the theta. So let's see, is it correct? Yeah, 21.1. Look. So we calculate the theta. Then, after we calculate the theta, we transfer the voltage and current to dq, that vd was something, bq was equal to 0, and then id and iq also calculated. So we need to see that our system is working well or not. So for this case, we said that we calculate the reference current minus the injected current. What is the injected current? Current injected from the grid. So we use this injected current and convert it to the D and Q, and we also have the reference current, and we just subtract and see that delta I obtained. So if delta I is equal to 0, it means that our controller is working well. Otherwise, it doesn't work. Okay? So to make sure that it works well, we came to PI controller and delta I from the PI controller, delta D ID in PI controller, and we create lambda D and lambda Q. Okay? Based on this lambda D and lambda Q and equation 23.1, 23.2, 1, 23.1 and 23.2, we had lambda, we had VDC, we had L omega IQ, we had VD, we had minus lambda Q, L omega VDC. So we calculate the lambda D and lambda Q. Lambda D, D and D, D and Q. Okay, switching. So we calculate we measured all the voltage value, current value, and then based on these two equations, we reach the ND and DNQ. Okay? So then we use the DQ to alpha beta to change it to DN alpha and DN beta. The reason for this is that when you use the space vector PWM, the input duty cycle should be, or switching state mode, should be in alpha beta and not DQ. And the reason is that when we go to a space vector, I don't know, should I explain to you why, or you accept it as it is? Explain it? Okay. So in a space vector, we have 8 operating conditions with 6 active actually. So this is this, it goes to this, goes to this, 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 and this. Okay? So this is beta alpha, no, beta alpha. So the vector started by 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, and again return back 1, 1. Okay? So it is combination of six, 60, 120, 200, 180, 240, 300, 360 degree. Okay? So up to here is, so when we have actually VA, VB, VC, and convert it to V alpha, V beta, the reference value will be V. Reference is equal to V alpha 2 plus V beta 2. Okay, so, and the theta is tangent inverse V beta to V alpha. Okay? So, if V, sorry? Is what? Radian. Okay, what is the difference? Degree or radian doesn't matter. If I say that 2 pi or 360, is there any difference for that one? I mean, basically they go in like this. It's started from like this. It started from 0 to 2 pi. But it's like it's 360. Yeah. Mm-hmm. Yeah, it's like, yeah, like this. So it's like this. Like this. Okay. So if we get like I don't know, 87 degree instantaneous value of the angle of the grid. So it means that the converter reference voltage is here, 87 degree, not here. So the switching method in this is different from here to here. Okay? So for this reason, when we jump to the alpha, to a space vector, then duty cycle d alpha and d beta first go to the tangent inverse d beta to d alpha, then provide the sector is between 0 to 60, is between 60 to 120, 120 to 180, 180 to 240, 240 to 200, 300, 300 to 360. So based on this theta, you choose that which switching should be applied that time to the converter. So if the theta is 278 degree, it means that we should use this sector. So it goes to here. And the switching should be chosen by this, not by any of these random actually. So for this reason, for the alpha beta in a space vector, we normally transfer the duty cycle from, or switching state function, from dq to the alpha beta and give it to a space vector. Then a space vector decides to go to which switching actually sector. We call it 6 sector, and based on that, they provide the switching pattern. So based on that, they provide the switching and 6 signals goes, which is complementary. So if this is 1, this is 0, this is 0, this is 1, something like this. So each leg have 2 transistors and they are complementary. So by this assumption, we provide the power to the grid. And these references can be chosen based on what you are going to do. So it can be simply said that reactive power is equal to 0 and active power is following like this. It depends what you are looking. But here mentioned actually in this discussion here we had. So now you learn easily how to integrate renewable energy sources to the grid by controlling power converter. And I believe that if you check your teaching material plus getting back to this structure, I can say that at least for the first time, 50% of the stage can be handled by yourself. Am I right, Siddhant? Now, if you can come explain, 50% of your discussion will be positive, correct, yeah? Would you like to try to explain that what is happening here? Yes? Okay, good. This is Indian yes or it's real yes? Because Indian. No real yes. Because Indian I said that they are very kind and always say yes, yes sir. So this is why I'm saying the Indian yes. Okay, good. Good to hear it. So now, if you feel that it is clear for you up to here was completely okay?
In each sector, one state is for upper lane and one switching state is for lower lane?
No, switching state is different actually. You should find the vector. Okay, so when the vector is here, for example, here, then like here, okay, then you should modify actually somehow the other voltage in D axis and in alpha axis in Q axis, and based on that you see that what is the actually I don't know how to say what is the value of, for example, here when you have first sector, okay? So this is your first sector, okay? And the vector is here, yeah? And then you have V alpha, and then you have also V beta, okay? Then you should calculate this one. V alpha is equal to V cosine theta. Okay, so based on that, you need to provide the switching time. Okay, if you need the detail, I can provide later, but switching time, it means that this, when we reach in this point, the switching time when we use this 100 should be, I don't know, Ts times 2 cosine something, okay? So by this, you provide the switching period. It is not like a 60 degrees, like a PWM, no. 60 degrees, 60 degrees, 60 degrees. No. We provide the value of the TS in each time. So then for also this part, and then when we reach to here again, we calculate the T for that one and that one, and then it's a, I mean, I calculate, I had the 3-level converter in my PhD, and then we had, for 3-level converter, we have, it goes there like this. It goes, each sector will be like this. So in a state of have a, because we had 4 transistors. So in a state of have a 1, we had 1, 2, 3, 4 in sector 1, between 0 to 60. So each one had also 3 switching time. So it means that for each sector, you should see that your vector is here, 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 or here. And based on that, you should choose that, you know, this switching for what portion of the time can be applied for the control. I remember that I did 120 subsection to calculate all the switching time of each transistor. So if you see that, you know, the vector is here, then you see that easily how much time should this one active, how much this one, how much this one, and how this switch also active between the different legs. So for this, you said that, okay, now my subsection is like between 0 to 60, 6 to 120, 120, 180, 180 to 240, 300, 360. Then when you reach, for example, you calculate easily theta, and you see that theta is here. Then you should consider that is it here, 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 here. If it is here, the switching is different, time is different, is here, is also the, and the worst case is that, you know, this vector is changing like this one, okay? All the time is changing. So all the switching time is like this one, okay? So it's not the constant value, you say that, you know. So by this assumption, you can easily, not easily, but you can provide the switch in the state function for your converter. But in MATLAB, you easily have access to the block. You don't know what is happening behind of that one. So when you are going to make the simulation, you chose the space vector PWM from the toolbox and put it here and give it the alpha and d beta and see it switch variable. Any questions so far? No? Yes? P reference. Yes. It can be anything, depend what you are looking for. But here in this case is based on what we discussed. We said that, for example, we can consider all the reactive power in fundamental frequency. So this is the all reactive power. And we said that actually we need the harmonic part. So this is harmonic part in active power, okay? So all reactive power and harmonic part from active power, and some part of the active power in fundamental frequency. So what we said here, say that, you know, you inject the all reactive power in fundamental frequency and harmonic frequency, and all active power in harmonic frequency, and some part of the active power in fundamental. We see the result now. I show you. You will be understand it better. But do we have any question? No? Is it complicated or so easy? Rakesh, is it complicated or so easy? Complicated. Which part is complicated that I don't know? Okay, let's see, and I get back